The last example of linear waves is going to be the topographic waves. So once again, I'm on the cluster. I'm going to go in the example directory. I'm going to go in the shallow 2D. I'm going to go in MATLAB. And I'm going to have to, again, change the grid file in order to account for a sloping topography, which is going to provide the restoring force for these topographic waves. So I'm going to open the topography. And I'm going to put myself again in the F-plane, so no Rossby waves. And I'm going to enable now a sloping topography here by saying that the topography is h plus a slope alpha, which is the h dx times y. So you can see this alpha in character is a derivative, exactly like the beta. And in fact, if you look at the dynamical equations, the sloping topography and the sloping or if you like the sloping f come into the dynamics in the same way. So in fact, these two are give rise to waves that have the same type of characteristics or properties, if you like. So now we're going to look at these topographic waves, and in this particular case, the slope is alpha is going to be defined as positive. It's a positive slope, so that means that you're going from in the southern part of the domain. Actually, let's just plot it. Why don't we just so I'm going to save that. I'm going to create um, I'm going to run MATLAB, and I'm going to create this. Okay, and now I'm going to pcolor grd.xr, which is the distance divided by 1,000 to have it in kilometers, grd.yr divided by 1,000, comma grd.h, which is our new topography. And I'm going to also put a color bar here so I can in the horizontal direction. Okay, so now you see that the bottom is still on average about 220 meters or so, and the slope now is going from it's increasing with latitude, meaning that you have lower topography and deeper ocean up here. Okay, so from shallow to deep. Okay, very good. So with such a topography, then, if you look at the topographic wave equations, what you'll find is that if you put a bump here, the topographic wave should move towards the eastern boundary. So it actually moves in this particular case in the opposite direction of the Rossby waves. Now, of course, if the slope was reversed, they would move in the same direction of the Rossby wave towards the west. Okay, so for this particular example, with this slope, that goes from shallow to deep, the topographic waves are moving towards the east, and you can look at the phase speed of these waves or the dispersion relationship to convince yourself. Okay, so where the initial condition don't change, they still have a bump in the middle of the domain, so I can run the script, but it's basically stays the same. And once I've done that, now I will run again the model by using the run model PBS command. And after the model is run, I'm going to move my output, my history files, into his underscore alpha dot nc, where alpha stands for the fact that now I have an alpha sloping topography, and I'm going to move the average file in here. Okay, so that's the two things. Now, one thing with the parameters that I set here, I create grid. I'm just going to create the grid one more time. But with the parameter that I set here, the speed of this topographic wave is actually going to be slower than the Rossby wave, and it's going to be about 47 days. Okay, so we should see these waves move slower than we saw for the Rossby waves. Okay, so once again, we can plot the solution by using this plot alpha. Okay, F12. Yeah, let me just edit this 1 second because I only want to plot the alpha solution, which is down here. So I'm going to comment these lines. So the history file is his underscore alpha and average G underscore alpha. Okay, so let's plot that, the alpha waves. Okay. Okay, so let's make this window a little bit bigger. Okay, and let's press return. And once again, we have the bump and the initial transient adjustment. In the time scale of days, you can only barely see the initial gravity waves, but the bump really stays in location, and there's some geostrophic adjustment that is taking place in the bump. And so this is the transient solution, moving very fast. You see the noise of these initial gravity waves again. And now we're going to look at the slow evolving part as soon as this is over. Okay, press return to continue. I'm going to press return. And now this is the slow evolving part, and now you could see that it's moving, but it's moving slower. Now it's 12 days. You see it hasn't reached the boundary, and it should reach the boundary approximately to half of 47 days, which is right now already. And so you see it reached the boundary, and so now you have a similar wave that looks a lot like a Rossby wave, but moving in the opposite direction because of the sloping topography. In fact, now we can make another plot, which is we can take a transect along here and look at how this transect changes with time. And which is going to be this plot here. And now you see that in fact this wave is moving towards the eastern boundary, and you can see that it's slower. In fact, the tilt of this is steeper than the one that we saw for the Rossby wave. So you see it takes over, what is it? This is the first wave reaches in about 20 something days, which is half of 47 days, which is the time it takes for this thing to go from here all the way across the domain somehow. Okay, so we can also look at the final state of the solution, which is the last figure, I believe, here. Okay, and so here you see again, like in the case of the Rossby wave, this topographic effect is basically equivalent to a slowly evolving unsteady geostrophic balance, and in this case it follows the wave, and so you could see that slowly the bump has been moving towards the eastern boundary, so eastward, and so you could see that there's no one single bump, but there's a whole bunch of different bumps, and if you look at the dynamics, for example, in this sea surface height here, you'll find that locally there is a quasi-geostrophic adjusted solution associated with this bump, but on a slower time scale the bump is also moving towards the east. Okay, so the geostrophic adjustment probably takes about a couple days to adjust, but the bump moves slower than that. Okay, so this is all for these topographic waves. Now, one interesting example would be one in which we could configure a model, for example, in which the topographic waves are moving at the same speed of the Rossby waves in the opposite direction. And let's do such an example. Create grid. Okay, so in here I'm going to in the grid file, I'm going to re-enable the beta parameters, and now I'm going to make my alpha parameters such that the phase speed of these topographic waves is the same as the Rossby waves. And to do that, I'm going to go here, and I'm just going to solve this equation so you can do the math at home. I'm going to remove that. And if you look what I'm doing here, I'm computing alpha such that the phase speed is equal to the c underscore r, which is the phase speed of the Rossby waves, and but in opposite in sign, so that it goes in the opposite direction. So now I can recreate this grid here, and you can see now that from here that the Rossby wave speed is 15.7 days, and the topographic wave speed is also 15.79 days with these parameters, but it's, as I said, is directed in the opposite direction. Now if you then perform the model run and you plot the solution using this alpha wave scripts, I call the solution in this case alpha beta. Okay, so I'm just gonna uncomment this. Okay, so now the history file and average file for this solution where both alpha and beta are present is called his underscore alpha beta and c. You can call it whatever you want. And if we now plot this, we'll see what we expect is that the two effects should be opposite to each other, and so the bump should actually remain in place. Once again, first we do the transient solution. This is in the early days. again, you can't distinguish anything. You see these inertial gravity waves going around, and we have to wait until this finishes. And so anyway, you see this noise going around. And now we can look at the slow evolving solution. And now in the slow evolving solution, you see that the bump is not moving. And that's because the Rossby waves want to go in this way, but the topographic waves are pushing the bump in this other way. And so this basically, it's an arrested wave that, because of the double effects of the planetary F, the change in F, and the topographic slope. In fact, if we now do a transect across the bump as a function of time, oops, it's right here, we find something that's very similar to the F-plane waves, which, where the bump is really not moving. Although by eye it would seem like there's a small tilt in this direction, but probably it's my eye. Anyway, and if we look at the final state of the solution, we find again that the bump remains in place, and that the solution is locally distrophically adjusted. Okay, although you see some detortion, if you like. Okay, so this is all for these topographic waves, and in this case topographic and planetary waves together.